this is the 6th edition of our Trace Talks podcast, and I'm thrilled to have Atar here as well as you here, Rick. And it's just nice. It's nice to have experience in the room. So
It's nice to be here. Thank you.
Yeah, so I'll let you guys introduce yourself. Rick, why don't you go ahead?
I'm Rick Hartley. I've been in the world of electronics. This coming February will mark 60 years. I've been in printed circuit design for the last 50 years of that 60 years. And I actively worked full-time for 40 years of that 50 years for various companies, originally for manufacturing companies, later in the avionics world, and then the telecom world, then back to the avionics world. I've done mostly for the last 50 years printed circuit design. I've helped with some circuit design, but mostly printed circuit stuff. And I do a lot of consulting and training in the world of printed circuit design, and that's pretty much who I am.
That's wonderful. It's a great experience. Nice,
It's
nice
it's a
balance.
lot of experience.
It's a lot of experience. And it's really nice that you're generous with your experience and your
Thank
knowledge.
you.
Yeah.
I appreciate that a
Yeah,
lot, and
yeah.
I try to be.
Yeah, that's great. That's really
Yeah.
good. Atar?
I'm Atar Mittal, and I have an electronics hardware engineering background going all the way back to 1970, so about 54 years of working as an electronics hardware engineer. And,
Nice.
And I entered the field at the time when the digital ICs, gates, and some of the operational amplifiers were just coming in.
Right.
And the tubes and the old things were just going away.
I'm sure you remember the 741 op amp, right?
I have played with 741 and used it so many times. I
Right.
still remember the pin numbering of the
You and me both.
741.
You and me both. I designed a lot of circuits with 741s.
Exactly,
Right,
exactly.
right.
It was, I mean, to design, high frequency filters, low frequency
Yep.
filters, and all those kind
Integrators,
of things.
all that
with the
holding
gain.
together,
I mean,
yep.
it was a heaven.
Yes, it
And
was.
I still remember the op amps which used to come prior to these ICs, which used to be bricks. Kind
Yes,
of
yes.
construction. You
Yes,
remember that?
yeah, they were like they were like 2 inches square, right?
Exactly.
And they were potted in epoxy inside the brick.
Oh boy. Oh
Yes,
boy.
yes, I remember those. Yep, absolutely.
Actually, in 1971, I designed a 12-bit analog to digital converter
Ah,
out of 21 circuit boards
real, my God.
in a
20
chassis,
21.
90 circuit boards. And since the very precision resistor ladders were not available in those days,
Wow.
Vishai was the only company which used to make 0.001% accurate resistors.
Wow.
And you needed that to
Sure.
have the 12-bit accuracy.
Yes,
Oh boy, I mean it was.
that's fascinating.
Of
That
course.
is fascinating.
4 or 5 years later, the ADCs started coming as ICs.
Right, and now they're just tiny little modules you put on a board.
Right.
Yeah. All
So-
the way up to 24 bits.
So exactly,
Yes,
24 bits, of course, is a little bit high end.
yes, yes, it's high
Most high
end.
end.
It's high end.
Yeah. And so most of my career has been spent in electronic design, digital circuit design, system design, and since the Sierra Circuits era from 2002 onwards, I have imbibed hell of a lot of PCB technology. Earlier, I was a PCB user. Now we have become a PCB technologist and all that. And what are the
Yes.
materials, properties, various frequencies, various stack ups, etc., manufacturing implications, and all those kind of
Right.
things. And of course, electronic components and the assembly.
Nice.
Okay.
Yeah, that's a good introduction. So thank you both for being here.
Thank you.
I'm going to dive into ground plane design and ground bounce. So simple questions first, if that's okay. So,
Sure.
well, Rick, we'll start with you. So how do you manage ground bounce in a PCB with fast switching?
But first of all, what is ground bounce?
Yes.
Yes.
Yeah, what is ground,
Ground bounce occurs, actually, ground bounce is exacerbated by the printed circuit board, but it's not a result of the printed circuit board. Ground balance is a result of high inductance in the pins of ICs. When you feed energy into the power feed on an IC through the output transistors back through the ground to the power source, the inductance of that connection through the output transistors, when they turn on and turn off and you ask for a lot of energy quickly through that inductance, you get a voltage drop that leads to putting a spike on the ground plane, and in some cases on the power bus. And those are called VCC and ground bands, and they're mainly the result of high inductance in the ICs. Now, high inductance in the circuit board, if the grounds aren't designed properly and the board doesn't have a good stack up where power is next to ground somewhere in the board stack up through a thin dielectric, will just exacerbate the problem because that adds to the inductance that's already the problem.
So the longer the
connection,
the connection length
right,
between the power delivery network and the consumption points,
right,
the more inductance.
that's
it will
correct.
have.
Inductance is a function of three things. It's partly a function of size of the conductor, but actually I was taught in college that inductance is more a size thing than anything, and that's not true. Inductance is more a length thing, as you just pointed out,
Right.
and a proximity thing. When you move energy in a circuit board, as I'm sure you know, you're moving it in the form of fields. It isn't about current flow. It's about fields moving through the dielectric space between the lines and the return path, in this case, usually ground. And the closer those are together, the tighter the control of the fields, but most of all, the lower the inductance. So it's tight proximity. Pins of an IC, having grounds near the signal pins, lowers inductance.
So basically what you're saying is that the loop area is important.
The loop area
The
is
smaller the
important.
loop area, the smaller will be the inductance.
Yes, that's correct. So its length and loop area are the two dominant factors. And a lot of ICs, many of them actually, are designed without enough power and ground pins, and the end result is they have high inductance lead frames, and they suffer badly from VCC and ground bounce. And I
So-
see it all the time.
So, as a designer or PCB designer, when you're selecting your components, you should be aware of these things.
Absolutely, and that's what I tell people in my classes. I've probably done 3 of the 5 classes I've done this week at the conference have talked about that exact issue, because I want to constantly drive that point home to people that this is important, and you need to know when you're choosing an IC, you don't just need a few powers and grounds in the lead frame of the BGA. You need probably as many powers and grounds total as you have signal pins. Usually about half of the total pin count should be powers and grounds, and the other half signal pins.
So does the size of the device also affects the amount
Yes,
of...
but not
Not
terribly.
that-
Yes, if the device is bigger, of course, the length is longer,
Mm-hmm.
and that, of course, will impact inductance.
Right.
But you can get a lot of pins in a tight area without making it a lot bigger. You know what I'm saying? Because there's an array of
Area
pins.
array.
Right, yes, there's an array of pins. So, yes, size certainly does make a difference, but less so that the important thing is to have an adequate number of powers and grounds in the IC lead frame.
And the frequency of this noise is
Oh,
pretty
that's,
high.
yeah, frequency is one of the dominant factors as well. And in fact, one of the solutions for ground bounce is to slow the signals down. So, and I don't mean to change the clock frequency, I mean to change the rate of change of energy, the rise and fall time of the IC outputs. If you can slow those down without impacting timing of your circuit, then you can reduce VCC and ground bounce, because you're putting less energy, you're putting the energy in a longer period of time. It's a dVdt, dIdt problem, right?
Right.
And when you can change the dIdt and the dVdt, then you can also reduce ground
But
bounce.
it is very difficult nowadays to get slower
Oh, yeah,
rise
it's-
time and fall times.
That's
because
right.
majority
Oh,
of the
are all
even
fast.
the
That's right.
gates are
Now,
designed for very high
the
frequency.
good news there, microprocessors and FPGAs often come with adjustable rise and fall times. They've realized what a serious problem this is, And so they give you the ability to slow it down if you don't need the fast edge for timing purposes.
This is wonderful.
That
news,
is one. Oh, you bet it's
because
wonderful.
I doubt whether a lot of design engineers are aware of this fact.
Probably not.
Probably not.
Well, it
Because
sounds important.
It is important.
That means the fundamental device is a very high frequency,
Right.
high speed device, but they have realized to introduce a mechanism within them to
That's
slow down the rise and fall time. Wonderful.
That's exactly right. Now, they ship it to you set to the fastest time.
Right.
Because they don't want to ship it to the slowest time. Because if you put it in your circuit and it's too slow and you have timing problems, you're going to blame them.
Right.
So they don't need that. So they set it to the fast time. But the engineers need to be aware they can adjust
And
that.
this is all done through programming.
Yes, it's all
I mean,
programmed. It's
introducing
programmable.
let us say, the extra capacitance to slow down the
They
rise and-
literally, I don't know how they do it. I'm not sure if
I
they're
think the
using.
capacitance
Probably.
is a semiconductor capacitance, and they may be having
Probably.
some kind of a connections over there, whether to introduce
So a
one
longer charge and discharge time, ergo.
Exactly.
Yeah, you're probably right.
Yeah. So that may be okay.
Wow. Okay. Well, that
And continuing on
Yeah,
that,
please.
you asked about
Right.
switch mode power supplies.
yeah.
Switch mode supplies that have the FET and the diode in the controller package are the ones that are most prone to suffer from ground and VCC bounce because the parts are in the IC package. And as you produce the fast switch, and now with a switcher, you don't want to slow down the edge.
True.
You can improve performance and you can improve EMI by slowing down the edge. And you can do that with a snubber. You can do that a number of ways. And those all work. However, it reduces the efficiency.
Exactly.
The reason we use switch mode supplies is to get higher efficiency.
Right.
Now, why would you destroy the efficiency just for the sake of making things work the way you want them to work?
No.
If you're going to do that, you might as well use a series regulated supply.
Because the time it takes to switch or the ramp up from one level to the other,
Right.
that is the time when there is a maximum heat
Power
dissipation takes
transfer of
place.
power, that's correct.
And so we need to, especially in the switching circuits,
Right.
switching more power supplies and
Right.
all that, you need to basically reduce that to
Right.
increase the efficiency.
That's right. You need the fastest rise and fall time you can get out of the FET.
Exactly.
So you don't slow those down. What you have to do is design the board and pick the package with good power and ground distribution and design the board so your power and ground planes are together in the board near the surface where they're going to be used and so on. It's a matter of circuit and circuit board design engineers thinking it through and doing the right thing.
Wonderful.
Yeah.
This.
Sierra Circuits has been working very hard for electrical engineers and PCB designers like yourself on our engineering tools. These are engineering tools to help you design faster. We want to reduce your design time and get the design right the first time. So our top tools on our website, number one is the PCB Stack-Up Planner. Knowing that you have a good stack-up right away for your design. Number two is the bomb checker. It'll do basic scrubbing, make sure your ref deses are good, your NPNs are good, the NPN matches the description. All these are amazing features of the bomb checker. We also have an impedance tool, which is based on Maxwell's equations. And these are all for free for the PCB designer and electrical engineer. Please go check them out. It's all for you. That's great.
Sorry to elaborate.
No, I think that was great, actually. I'm still digesting. It was really important. Okay, so I guess it actually segues into the next question. Just some layout techniques on ground plane design, for the switching regulators. You already said it, be close to it. And
Sure, absolutely.
have some ground and powers close to each other.
There are other things about
Okay,
ground
then tell us.
ground in switchers.
I
Yeah,
think
tell
you
us.
should.
Yeah, elaborate.
Yeah, and you just said it a second ago yourself. Have ground if you have your components and routes on layer one, have a ground on two.
Right.
That is of critical importance. I say that constantly in my classes. Layer two should be ground. Layer two should be ground, and I say it over and over. Of course, that helps a great deal. One of the things that's popular right now, and I was talking about this coming in here today that's popular right now is people think that the ground plane under the switch node, which is where the FET, the diode, or two FETs in some cases, and the inductor come together, that switch node should have ground removed under it because people make the pad of that switch node huge, and which I think is an assembly problem because you're trying to heat up so much copper, it's hard to assemble the board. But aside from that, it has other implications. And one of the biggest ones is when you have a really large pad, the size of your hand, and I'm joking, but some of these people make these things so large, it's insane. And you have that above a ground plane, it makes a massive capacitor. And that capacitance of that junction will tend to cause the fast switching edges to oscillate.
Exactly.
And so to prevent the circuit from oscillating, people cut out the ground under the switch node to stop the oscillation. But when you do so, you're causing fields to spread because now the fields don't couple to the ground. They have to spread out to couple to wherever the ground happens to be left. And all it ends up doing, and every time I've seen somebody do that, by removing that cutout, I've always been able to improve the EMI signature of their board, always.
Wow.
So what I tell people is, well, and the answer they give is, well, yeah, but I want to lower the capacitance. All right, don't make the pad the size of your hand. Make it only as big as it needs to be to solder the three components together and to carry the current in question. That's all you have to do.
Exactly.
And once people realize that, all those problems go away. So don't make cutouts in the plane. That's probably the biggest
So
suggestion I could
to
give.
basically remove oscillations, they are introducing additional electromagnetic and signal
That's
integrity
ex-
related issue. I mean, that
Yep,
is-
that's it.
That's not a very wise trade-off.
No, it's not a good trade-off. No.
What is the maximum acceptable trace length with impedance mismatches when routing fine pitch components?
And there's no one answer to
Yeah, there's no one answer to that question.
because it's really a matter of rise and fall time. It all comes down. It always comes back to rise and fall time of the IC output. When you have, for example, a 500 picosecond rise and fall time, that has an upper end harmonic frequency of roughly a gigahertz, and as long as every circuit has a point where it's lumped in length, and as it gets longer and longer, eventually it becomes a distributed element. Right. And once it becomes a distributed element, that's when you must control the impedance. So as long as you can keep it short enough that it's a lumped element, then you don't need to care about the impedance. So to answer your question, and I don't remember the numbers off the top of my head, but with a 500 picosecond rising edge, I think a line of an inch, inch and a half, maybe 2 inches. And again, I'm guessing because
I think it is roughly, I mean, you know, the famous book about the EMC compliance and all those things. It gives a rule of thumb, roughly that lambda by 12.
Yes, that's right. That's right. That's right. Okay, yes, that's true. And that's a good one. Thank you. Yeah. That's a good example. Perfect. Thank you. So in this case, a gigahertz, wavelength in a circuit board at a gig is going to be about 6 inches.
Right.
Because in air, it's a foot, right?
Right.
It's actually 11.8 inches, but let's round off. It's easier to do the math. So it's 6 inches divided by 12 is a half an inch.
Half an inch.
So basically, any connection that's shorter than a half an inch doesn't need to be impedance controlled. Anything longer needs to be impedance controlled.
But this is only 1 gigahertz. Nowadays we are talking of data transfer rates
no question about it.
Of 20 gigabit per second.
Oh yeah. At those frequencies, everything has to be impedance controlled. Right. Now that said, people put components on boards, and those components create impedance discontinuities. Right. And sometimes the discontinuity is long enough that it causes a reflection. Right. And one of the solutions, guess what one of the solutions is for that? Cut the ground plane out under the pads. But guess what that does? So, you have to decide what you care more about.
Right.
And the truth is, and I've discovered through my career, that small impedance discontinuities, as long as they don't create large, as long as the reflections they cause are just little ripples, so what?
A small blip,
Yes.
which is, let us say, much less in width compared to your bit width.
That's
The
correct.
data bit width.
That's
If
correct.
it is very small, let us say 1 by
That is
10th
right.
or 1 by 15th
A
or
little
something.
bit of ringing on a transmission line is
Is
not
okay.
is not deadly. A lot, of course, would be.
A lot.
So component mounting is less of a problem than people think it is, even at very high frequencies. Now at 20 or 30 gigabits, that may be an issue, and I'm not 100% certain. I've not worked at those frequencies yet, so I'm not certain the ideal solution to that. It may be to do a partial cut underneath the component pad, not completely under the pad, but maybe part of the pad to lower the impedance of that connection enough to get it closer to the transmission line impedance. That might be the solution. I'm not certain.
If it is happening at the end of the line, then of course terminations is the issue.
Oh yeah, if it's at the end of the line, who cares? And you hit it right on the head, because the termination device, if it has an impedance discontinuity in its attachment, so what? Because the energy is going to terminate into that device anyway, and you don't care.
You don't care. Exactly.
Right.
And if your source side is also matched correctly,
Right.
then your reflections are not
And you know,
that
you, you just hit on a key point.
Right.
When you series terminate, it's pretty much the same thing.
Right.
When you series terminate, you do what's called, as I'm sure you know, reflection mode switching, where the initial wave that comes out of the IC is only half of VCC.
Right.
It comes down the line, it doubles as it hits the last load,
Right.
and which drives the last load, and the energy reflects back to the source. If you get a little ripple because of a slight discontinuity in the attachment of that series termination, it's going to drive the line a little high or a little low. It's not going to care.
Exactly.
It just isn't going to care as long as everything functions properly in the end, and it will.
So basically, I guess is that it basically comes down to, from the way you are saying, is that it comes to what is acceptable
Right.
from your performance perspective, and
Right.
whether you have allotted the budgeting of the noise.
That's
Let us
correct.
put it this way.
And that's exactly right, because you have a noise margin to play with.
Right.
How much of the noise margin do you want to give up to reflections, to crosstalk,
Right.
to VCC and ground bounce, to power bus noise, and so on? And you have to decide what matters most to you. Some things you can't get rid of, so you just assume, okay, some of my noise margin is going to go to those little ripples, and that's just life.
So this is just like the normal economic life. And just like you budget your
Yep.
life,
Yeah.
your income and all
Yep.
your expenses. Similarly, this is expense budget. The noise is an expense.
That's
So you
exactly
basically need
right.
to budget it properly.
That's exactly right. Well said.
That's-
Maybe we can do another session on how to budget properly.
Oh yeah. Oh yeah.
It's a thought.
We
Right.
have to bring in some Wall Street guys over here.
Yeah, right.
Okay, so that was good. Do we want to talk about RF design?
Sure.
So I would say the number one design guide on our website is our RF design guide.
Okay.
So I think it's like just looking at what we see from our website activity, RF is becoming more and more of a hot topic. So, okay, a question I have here about RF is, when designing a PCB with an onboard or external antenna, what strategies do you follow to avoid coupling between the antenna and the heatsink?
Probably the best answer I can give to that is one way or the other, you have to keep the antenna completely away from the heatsink. There's just no two ways about it. There's no secondary way to handle that I know
Okay.
of. Antennas on circuit boards are usually not dipoles, they're usually monopoles.
Right.
And they generally reference the ground plane right at the edge. So you'll clear out an area at the edge of a board to build the antenna on. There'll be nothing under that all the way through the board. And then right next to it will be the ground plane that the antenna references.
Like coplanar.
Exactly. It is coplanar. And if you're going to put a heat sink on that, it needs to be completely on the other end of the board. You can't put something like that in a metal package.
True.
Because the metal package, of course, would destroy the performance of the antenna. People who use metal packages sometimes will even put a plastic end cap on the metal package so they can have the antenna in the area where the plastic is. But in reality, even the plastic attenuates the fields to and from the antenna. So there's nothing you can do to stop some attenuation. The circuit board will create some attenuation.
Right.
And for that reason, sometimes people put the antenna outside the system, with a little coaxial attachment. So the antenna.
And launch.
Yeah, so
And launch.
exactly. So it's completely independent. There's no absolute one answer to that question. But you must keep the antenna away from anything that can attenuate it.
But-
and that's metal, plastics, whatever.
Yeah. See, metal is a big,
Oh,
let's say, absorber of energy, electromagnetic energy.
or reflector, one
Or
of the two,
reflector,
depending
yeah.
on whether it's
And
magnetic.
therefore, a heat sink is metallic.
Yes,
And a large metallic body comparatively to any other metal on the PCB.
that's correct.
And therefore, it's going to spoil the performance of the antenna
Yes, it will.
if it is very nearby.
So it's a proximity thing.
Yeah.
You just don't have a choice. And I've seen people make that mistake
I think
and then wonder why it didn't work.
question arises out of that is that the good thermal design
Yes,
is extremely important at the same time,
it is.
because do you really need the heat sink, or can you manage the thermal,
Right,
let us say the heat removal
right.
and the cooling, effectively through thermal vias and all those kind of things?
And sometimes you can.
Sometimes you can.
But if you do need a heat sink,
Right.
probably the best way to handle it if you have a metal package
Right.
is to put the part that needs to be heat sunk on the opposite wall as the antenna and use a heat sink that can be attached to the metal
Right.
so you can use a smaller heat sink. So you use the heat sink to pull the heat out of the IC and then into the back wall of the enclosure to get good distribution of the heat.
Wonderful.
That allows you to use a smaller heat sink. We used to do that all the time in telecom.
Right.
And we were able to keep heat sinks completely away from things that were more critical, like I/O and that sort of thing.
No, I think that's a very smart.
Yeah, it wasn't my idea. I wish it had been, but
That's interesting. So yeah, no. Yes, in RF design, an engineer needs to make all these types of choices. But in every design, it's the same choices. But it seems like in RF design, the choices, if made improperly, are even worse.
they're devastating.
They're devastating. Yeah.
Yep, that's true.
The signal integrity implications in RF are far more prominent, and
Yep.
they can, decrease your performance
That's
quite
correct.
a bit
Yep.
compared to, let us say, less than RF. kind of
Digital has a much broader noise margin,
right.
hence a lot more leeway to have mild noise or do things wrong at times.
Sure.
RF, no room for that at all.
Does the material selection here makes a difference?
Oh, in RF, huge. Sorry, hold on. It makes a huge difference in material selection because some materials are much lossier than others.
Right.
FR4, though it's a wonderful material,
Right.
is a fairly lossy material. And I've had people say, oh, come on, it's the 345 gigahertz, you can't use FR4. Well, you can if your lines are so short.
If your board is very small.
And the lines are very short.
Right.
Then the amount of it's still gonna be more loss per millimeter, but as long as you have very few millimeters of length, the loss still may be within an acceptable level. But the point is, if you have long RF lines, then you're probably going to have to go to a lower loss material, like a Rogers 4000 or the Arlon or Taconic equivalent of those,
Sure.
or one of the other high-end materials.
Yeah, Panasonic.
Matsushita, Megtron 4 or 6. I mean, there are a number of materials, depending on whether the design is digital or analog.
I think Rogers have come up with a pretty good set of such materials.
Rogers
and so
have.
has Isola also.
Oh, yeah, Isola
Tachyon
and
all
Arlon,
those,
too. Yes, absolutely.
all
All
those
of those companies
Right.
have done a really good job of coming up with really high-end.
low dielectric losses.
You betcha.
Yeah, oh.
And tightly controlled dielectric constant
Exactly.
so that you get good control of impedance, provided you keep line widths and height above the plane reasonable.
So for basically at RF and higher frequencies, the constancy of the dielectric constant versus frequency is also very critical,
Yes.
because that can introduce additional losses and
Yes, it certainly can.
and-
That is true.
True. Okay. I think the PCB material manufacturers are coming up with pretty good materials nowadays to basically.
They
address
certainly are. In
that-
fact,
these kinds
I did a class yesterday at PCB West
Mm-hmm.
on attenuation in very high-speed circuits.
Right.
And on one of the slides, I had a list of 8 or 10 materials
Right.
that I've used in my life that are common, starting with FR4, then going to 408, then going to Megtron 4 and 6, and all those, down through this long list of stuff, ending up at Tachyon 1000 or 100 or whatever it's
Right.
called. Yeah. And I said to the group as I presented this, when I put this thing together a few years back, this was probably half the materials available. Today, there are probably 100 or 200 really well done, very high quality, high speed, and RF materials available for people to use.
Right.
And I said to everyone in the room, talk to your fabricator.
Exactly.
Don't guess, don't assume, talk to them, see what they use, because after all, you have to have it manufactured.
Yeah.
And if you're going to pick a material, if you pick Megtron 6 and they have never worked with it, it could tie up their hands, to say nothing of the fact that it's going to extend the time to get the boards.
Right. Yeah, I wanted to weigh in on that. So as a PCB fabricator, the selection, the deluge of material options, it's becoming overwhelming. Thank you for listening to our podcast. The podcast is for you electrical engineers and PCB designers out there to learn from. And we also have an amazing discussion forum that we recently launched called SierraConnect. So go there right now, post your questions, and industry experts will respond to your questions. It's an amazing resource that you should take advantage of.
In Sierra circuits, what we have done actually to some extent is basically equivalency.
Mm-hmm.
So we are trying to basically create an equivalency chart.
Mm-hmm.
Okay, these subgroup of materials
Right.
are capable of being exchanged between
Yes,
them.
and
So-
that's a good point.
yeah.
That's a great point.
And it reduces the multiplicity of the kind of see, when you want to, a PCB manufacturer is expected to stock the materials so that they are readily available to
Right.
the electronic engineers when they need them.
Right.
And at that time, if you're stuck up with a material which, let us say, due to some reason or maybe due to some international situation or whatever, you are not able to get that material, for example,
Right.
then in that case, you need to have solutions.
Right.
And those solutions are very important from the point of view of
When I was at
equivalence.
L3 and we were designing RF stuff, for example,
Right.
we didn't usually specify an exact material. We would specify the parameters we wanted the material to meet,
Exactly.
knowing that there were multiple brands that could be utilized to hit that exact point, and put a note on the drawing that said, meet these qualifications, and ask the fabricators verbally, when you choose a material, let us know what you've chosen so we can take a quick look to make sure we're happy with it, and then we'll go with it.
But sir, that era is gone.
Yeah.
You see,
Why is that gone?
see, I have this feeling that most of the new designers, they go by the application notes and whatever the
Yes.
the literature,
I want you to use this exact material.
exact material,
Yeah.
and they don't go into the details of the
Right.
material properties and all
Right.
those kind of
Yeah,
things.
the younger
Yeah.
generation
Yeah,
needs
yeah.
to
I
learn
think it's
this.
the lack of, let us say, attention to detail on the material properties,
Right.
which is leading to this.
They pick a brand name and a part number, and they tell you use this.
So finally, it falls into the lap of the PCB manufacturer to
Every
suggest the
time.
solutions.
Every time.
That's what happens.
And what designers don't understand, and I know you guys are going to go true about that, is it drives price up.
Yeah,
Right.
very
Because
true.
if you don't stock that material, now
Right.
you've got to go out and buy it.
Right.
And you're going to be buying it in small quantity, which means, guess what? You're going to pay a lot.
Yeah.
And then they have to wait maybe a week or two or whatever before you can even start the boards.
That's right.
True, true.
Designers need to be wiser.
Yes. I like that statement. Be a wiser designer. I love it. Okay. let's switch over to more EMI EMC talk. Is that okay?
Sure.
Okay. I'll throw an easy one. How can you reduce the parasitic inductance and capacitance of vias in high-speed boards?
That's a great question. Almost every designer I know, well, that's not true. A lot of the designers I know believe that making vias larger drastically reduces inductance. Now, in truth, it does lower inductance. But two vias in a 62 mil thick board, 1.6 millimeter thick board, that are 10 mil drill and a 20 mil pad that are a 1/4 inch apart will have an approximate inductance all the way through the board of about 2.5 nanohenries. If you make the vias twice that size and leave them a 1/4 inch apart, the inductance will drop down to about 2 nanohenries, which is a reduction of about 20%. But that's all it is. If you take those two small vias, instead of leaving them at a 1/4 inch, put them where they're close enough together that the pads are separated by 8, 10, 12 mils, the inductance of those two small vias will drop all the way down to a nanohenry. So they go down. Yeah, it's a huge, it comes back to what we said a little while ago. Inductance is a proximity effect more than a size effect.
Right.
And that's why people think, oh, lots of vias, really, and that's another mistake people make. They'll put power via, power via, power via, power via all next to each other, thinking that lowers inductance. All that does is drive inductance up, and I don't have time to explain why because it's really deep, but it's called the solenoid effect.
Right.
You need to do power, ground, power, ground, power, ground. You need things in pairs, and you need to exchange power next to ground, next to power, next to ground.
Loop area
You're
reduction.
creating small loop areas. Thank you. Well said. It's exactly what
That
it is.
is what is required.
It's all about loop area. Yep.
So
Well,
in-
that's priceless information.
Yeah, no, I mean, this is something which is, let us say, this solution is extremely important, and I doubt whether people are aware of that.
No, I doubt they are either. I see people all the time
Right.
with bulk decoupling, like the 20, 30 microfarad caps that are big.
Right.
They'll put 3 or 4 power vias next to the pad at one end, 3 or 4 ground vias at the other end, and think they've lowered inductance. That does not lower inductance. That just causes problems. It doesn't solve them.
Wow. That's good. It's good to know.
And all these things, I mean, the more inductance, the more electromagnetic
Of course.
noise.
Of course. And the more drop you're going to get across that
And more
inductance
drop, right.
as you try to move energy in and out of it.
Exactly.
Yeah.
I have one question.
Please go
here
ahead.
on-
Go right
on a
ahead.
related topic. See, we're talking of the component layer, and the next layer is the ground plane. and all.
Yes. Yes.
But in lot of, high frequency analog, especially RF designs, they try to have a ground plane on the top, on the outer layers, etc., to do a shielding effect for the electromagnetic interference and EMC compliance or whatever it is.
Right.
Now, how is that? How do we reconcile that with the ground plane on the number 2 and all that stuff?
I'll tell you why that's done.
Right.
We used to do that sometimes.
Right.
Some of the RF boards that we did, both at Goodrich and at L3 when I worked at those two places, we would have RF components and routes on layer 1. Now, the reason for routing on layer 1 is you don't want to have to apply a via to the thing to get to an inner layer if you can avoid it. That can be done if it's done properly, but going through a via can create its own set of problems. So
Sure.
keep the route on layer 1 from destination to, or from source to destination.
Right.
And we would put a ground plane on layer 2. We would copper pour on layer 1.
In all the unused area.
In all the unused areas.
Okay.
And we would attach it to the ground plane on 2 with lots of ground vias.
I mean, some stitching
Yes,
vias
yes.
at the right distance.
Guess what? Every 12th wavelength,
Exactly.
right?
Yeah.
And the reason we did that was to create, and we would make the coplanar copper really close to the traces
Right.
to create what's called a coplanar waveguide with ground, CPWG.
Exactly.
And the advantage of that is all of the electric and magnetic fields are captured in the cavity just below the trace, and between the vias and the ground plane on
Right.
two, you have this, it's almost like a waveguide cavity.
You
And
box
all-
the electromagnetic waves.
Yeah, we're making a
basically.
waveguide. We're producing a
Exactly,
waveguide.
effectively.
Yeah. It's not just a transmission line, it's an effective waveguide.
Wave.
And so you often see ground on layer one of an RF board because people know that that's what people who know what they're doing do. And sometimes people who even don't know what they're doing will put a ground plane there thinking, well, I have to do that. Well, you don't have to do it, but if you do it correctly, it can be beneficial.
Right. Yeah, I mean, yes, the what do you call the flooding with the ground plane?
Yes.
The unused areas, but make sure that these are not. They have to be properly terminated to the ground through vias, because any area which is not terminated properly possibly can increase the
That's it will,
The
because
electromagnetic,
that
emission.
unterminated plane area will actually have a different voltage potential than the ground plane below.
Right.
And so you're actually creating a voltage difference between the two that you don't want. So yes, you have to make sure the two are terminated properly together. Every 10th wavelength is enough, 12th is ideal.
Yeah.
But if you have something that comes to mind, please,
No.
be
Please
my
carry on.
guest.
No, carry on.
So for DFM, basically manufacturing, what do you think a fabricator should follow, and an assembler, to minimize any kind of ill effects? Especially for, let's say, high-speed boards or RF boards, or just to minimize EMC. Do you have any thoughts on that?
Obviously, it has to be a fabricator and an assembler who knows what they're doing. Because with high-speed boards, whether it's impedance control or just controlling EMI, the traces have to be the right width to meet target impedance. The dielectrics have to be the right thickness to meet target impedance, and so on. And so the fabricator obviously has to follow the documents provided by the designer. However, I always throw this back on designers, because it's up to the designer to make sure they know what they're doing. And far too many that I've met don't. And what I tell them to do is contact the fabricator and ask him, what I generally do when I'm designing a board, I'll use a field solver like the Polar 9000, which is my personal favorite.
Or the Sierra Circuit's impedance calculator on the web.
Yeah, or that's correct. You can do that as well. That's a good thought. I hadn't thought of that. That's a great point. I'll use some kind of quality calculator to come up with what I think is the right line width versus height above the plane, assuming that the dielectric thickness of that FR4 material is going to have the dielectric constant I think it's going to, because I may not be right about that.
Right.
I may have made an assumption that's incorrect. And I'll design a controlled impedance transmission line on a board, 8-layer board, 10-layer board, whatever. And then I'll send that to the fabricator and I'll say, here's my proposed stack up. Here's what I'm guessing we're going to have in terms of dielectric thicknesses. Please correct anything that's wrong. And I'll have them readjust dielectric thicknesses and copper weights in case I've screwed up something there. If maybe I made a choice of 1 ounce copper in a place where it should have been ½ ounce because of etch of lines and that sort of thing. Or on an outer layer, maybe even 1/4 ounce to be able to achieve 3 and 4 mil lines, which is what is, as you guys know, is necessary.
It's necessary.
And I'll ask them, please make any corrections necessary and send it back to me. When they do, I will then double check to make sure their line width, using the same calculator, whichever one I use, now meets my impedance requirement. And if it does, then I design the board. I put that information on the fab drawing, reminding them that they were involved in the choice of the design of this board.
Right.
Which is one way of saying to the fabricator, make sure you produced it this way.
Absolutely.
So that's it's really more of a designer responsibility, but once it's designed correctly, it's up to the fabricator to then produce that board correctly.
Right. See, the manufacturer definitely needs also some allowance,
Of course they do.
permission to basically correct, make adjustments within given limits
Right.
to make sure that the material dielectric constant and
Right.
the dielectric constant of a material is dependent on the resin content and its construction and
Glass
so
to resin ratio.
so you can't have the FR4 sheet which is given in the IPC,
Yes,
the sheet
right.
over there standard. That is only for 50% resin content.
That's
and of
correct.
particular thickness.
Right.
Yeah, that's not valid for all kinds of prepregs or
I-
cores.
I tell people that all the time.
Right. So that I think is a very important point.
It
that
is. You have to work with the fabricator if
Right.
you expect the right result. That is the bottom line. And engineers and circuit board designers who don't do that are kidding themselves.
So a stack-up design becomes very critical.
Oh, it's the most important part of the
Most
design.
important part of the design.
And the truth is, people who, when somebody calls me with an EMI problem
Uh-huh.
and says, hey, I'd like for you to look at our design, the first thing I ask them, what is your stack up? Where are signal layers, where are plane layers, and what are the plane layers? Because, honest to God, 75% of the time, the problem is in the stack up somewhere.
Right.
It's amazing how many people screw that up.
I know.
It's just amazing. I'll see designs where they'll put 3 power planes in a row with no ground planes anywhere nearby. I'm telling you, you will not get clean power delivery from that. Every power plane must reference a ground plane. It must. Not a maybe, that is an absolute.
Power integrity is absolutely
Oh.
essential.
Today, in this world,
Right.
power integrity, when it's not done correctly, is one of the biggest causes of EMI.
EMI as well as signal integrity.
Yes, absolutely. But EMI just jumps off the page at you.
Excellent.
I mean, that's Lee Ritchie was at the conference yesterday doing
Mm-hmm.
the power integrity class.
Mm.
And I know he says that in his class because I know he's experienced it like me
Right.
multiple times, seeing an improper power bus cause an EMI problem.
Exactly.
It's amazing.
So EMI, signal integrity, and power integrity basically go hand in hand.
They have to go hand in hand. If they don't, you're in trouble.
Right.
Yep.
So, would it be proper to say that if you have taken care of signal integrity and power integrity aspects in your design, in your stack up, in your material selection, in everything, then to certain extent you have also suppressed the EMI
That is correct.
radiation.
It doesn't mean you won't have an EMI problem.
Right.
Because EMI problems depend on the standard to which you have to meet. I mean, for example, the standard we had to meet in the avionics world, if that board whispered, you were in trouble. And the same thing is almost true for automotive under the hood.
True.
I mean, you talk about a tough nut to crack. My God. And those people are constantly, I mentioned this the other day in the session I did.
Mm-hmm.
If you ask management in an automotive company, what would you like your circuit boards to be? They say, oh, we'd like for it to have 0 weight, 0 size, and 0 cost.
Huh.
I mean, they want, and there's an expression they use, who do I have to kill to save that penny? And of course, they don't really mean it, but they really are constantly driving their engineers to put less into it to get more out of it. And that's not, there's a point where you can't do it anymore.
So what you just now mentioned is very important. The automotive industry, electronic applications, and in aerospace and all that are
Yeah.
critical areas
Yes, they are.
for the EMI.
Yes, they are, because they're so, you have to meet a much higher standard.
Much higher standard.
You just have to. It's that simple.
And
Aircraft avionics just can't be interfering with one another.
Right.
Let's be honest. Pilots get really upset when the nav system stops working.
And similarly for the driverless cars.
Right.
Which
Oh,
Mr.
yes.
Which
That's
Mr.
a
Musk
real-
demonstrated a auto taxi or something like that.
That's
Yeah.
right. That is
yesterday-
another very good point. These driverless cars, those circuit boards and circuits must be nearly perfect.
This
Yeah.
is
No pressure to any
Yeah, no
design.
pressure here. When I first went to avionics in 1991 and saw how severe the pressure was there, I was surprised. And the first circuit board I designed there, I used the standards to design that I had used in the industrial world.
right.
And in the industrial world, we met EMI standards easily. And the first circuit board I designed failed miserably in the navigation world. And it's because they had to meet a much higher standard than I had ever been used to. And I learned new ways of designing.
If you haven't heard of Sierra Circuits, Sierra Circuits is a PCB manufacturer and assembler all in one, located in the Bay Area, right around all the innovation that's happening. And Sierra Circuits is capable of building everything from start to finish, from simple standard product to uber complex HDIs, flexes, rigid flex, high-speed applications. Anything that you can think of, we pretty much can build, and we do it quick. So if you need to maintain your schedule and be on time, Sierra Circuits is your vendor of choice.
Is there any simple instruments or simple calculators by which, let us say, you can,
Determine the EMI signature?
Something like that?
Yes, no.
Okay.
People have been working on that forever. Mm-hmm. I saw an interview, probably close to 30 years ago, between Printed Circuit Design magazine and Tom Van Doren, who at the time was the lead research professor at Missouri University of Science and Technology, who probably led the world for years in EMI research.
Right.
And he was asked in the interview, do we have a tool that can predict EMI? And he said, no. And they said, do you think it'll ever happen? And he paused for a long time, and he said, it's such a complex matter, right. I'm not sure we'll ever fully achieve it. Now, AI may be able to help with that, right. Because AI can look at billions of things in microseconds that it takes humans years to figure out. And it's a matter of massaging and digesting enough data to figure out where that little channel is you need to follow to make this happen. To this point in time, I don't think there are any tools that can accurately predict it. What we have are rule checking tools. For example, you can't route across the split plane because that'll almost always lead to EMI. There are certain power bus design rules, where you put decoupling, how you attach it, all that kind of stuff, that can improve the EMI signature. And these rule checking tools look to make sure you haven't violated any of those good concepts. But even they don't predict EMI.
Right. So over a period of last 40, 50 years, the best practices have evolved.
Right.
How to reduce the EMI.
Correct.
And its impact, etc.
Right.
But the exact value prediction, the field strength prediction at a particular point or
right.
something like that, away from the board and all that, that is still a little away. And AI may be helpful in speeding up that.
That's correct. Yeah. I mean, it's a matter of knowing where all of the fields involved, because this is about field containment.
Right.
This isn't about current flow. It's about field containment. And where all of the fields are from all of the transmission events in a circuit board. And when I say transmission event, I mean power delivery. I mean transmission lines. I mean all of that stuff. Where all those are, those fields, trying to predict the impact not only that they're going to have individually, but on each other to predict what the EMI signature is going to be, very, very challenging. And to this date, not to the best of my knowledge, no one's accomplished that. But someday maybe.
Rick, you have popularized it, and you are very fond of saying, I've attended several lectures of yours in the past 6-7 years. Or even more longer, actually.
Yeah, it's been a while.
Since the PCB West started. So that the current the signal doesn't flow on a conductor.
That's correct.
It is because the speed of electrons and all those things, and the drift velocity and all that is very
drift
small.
Velocity.
Very small.
Correct.
And the electromagnetic signals which are traveling, your signal is traveling at the rate of roughly about half that of
the speed of light. And it's traveling in the plastic of the circuit board, not in the copper.
Right. So what is the use of copper? Can we eliminate that copper?
Oh,
No.
no, it guides the waves.
It guides.
That's the secret. I mean, yeah, you could, I mean, look at radio.
Right.
Radio doesn't have copper lines. Once the antenna broadcasts the fields,
No, but
they
this-
travel out through free space. But the problem is they travel in all directions. You know, if you had a circuit board, you could theoretically set up a circuit board with transmitters and receivers,
Right.
where you broadcast the fields in all directions and tune
And
each.
receive only a small part
Right.
of it, a
Right.
small strength of it someplace else.
Exactly, but you tune each receiver to pick up only certain waves. I mean, technically that could be done. It'd be a hell of a waste of
Very
energy.
inefficient.
Oh,
wastage
God.
of energy.
The waste of energy would be massive.
Right. And therefore, the correct way for engineers to think about it, interconnection is that it guides the signal.
It's a waveguide.
It's a waveguide.
Yes.
It's a waveguide. They're wonderful. I mean, this is very important because
Oh.
most people feel that your signal is I mean, that is what in common language we say,
Right.
that our signal is traveling along the in the conductor.
And it isn't.
It is not traveling in the
correct.
conductor, but it's traveling around the conductor,
Yes.
guided by the conductor.
That's correct. The conductor and its return path.
Exactly.
Because it's the two together that make up the waveguide.
Exactly.
Yeah.
Wonderful.
Yep.
I think that's and
It's really important. isn't
I
it?
remember maybe 10 years back, you were giving a lecture at PCB West, and I was there, and you mentioned that point, and there a lot of guys were wondering what.
Some guy said to me 2 days ago in one of the presentations I did, after I was done, he came up to me and he said, "You said something today that just changed my life, because you talked about where energy is. I've never known that, and now I understand." And if once you get that concept, suddenly everything makes sense. Ralph Morrison beat it into my head. I loved Ralph. God, what a guy. And he had to beat it into my head, because at first, I mean, I learned in college like everybody else that it's about current flow.
Right.
And I just didn't want to, I mean, I figured every engineer in the world can't be wrong. Ralph must be wrong. And he kept beating on me until he drove it into my head and made me realize, oh, he is right.
Oh, so
Yeah, I
you have
was.
attended college under Ralph Morrison?
Did what now?
I mean, was he one of your teachers?
No. I knew Ralph personally.
Oh, I see.
And I met Ralph through Dan Beaker,
Okay. Oh,
because Dan attended one of my classes over 20 years ago.
right.
And he came up to me afterwards and said, "You've really changed my thinking about stuff the last couple of days." And he started looking through the books he had on his shelf and saw one from Ralph Morrison and looked at it and thought, wow, this is good. This is good stuff. And he called, and he was trying to find people to speak at a Freescale conference at the time.
Right.
And he asked me to speak, and then he also called Ralph up and said, would you come to this conference and talk? And so Ralph and I and Dan all met at that time. And Ralph, absolutely, and I know Dan would say the same thing.
Right.
He
Ralph
does,
changed
yeah.
his life, and
Yeah.
he changed my life, I guarantee it.
Ralph, I mean, those 3-4 booklets, I'll call them booklets because they're not thick books.
Right.
The Ralph was writing thinner books,
Yeah.
not too many pages, but
Right.
the way he explains things
Oh.
in such a common way
Yeah.
is
The
wonderful.
last book he wrote before he passed away a
Right.
few years back, he died at age 94. The last book that he wrote is called PCB Design Energy Management, and it is the whole
I
book.
have that.
Oh, so do I. And unfortunately, I know Ralph would have given me one if I'd asked for it, but I didn't want to do that. I bought it online, and I wanted to get him to sign it, and unfortunately, he passed away before I ever got his signature in it. I wish I had it, boy. But anyway, it's a great book, as you know, because it explains energy movement
Right.
perfectly.
Perfect.
And once I understood I wondered why two circuits that had no connection to each other, why would one interfere with the other if there's no copper connecting them? And I never understood that, because I thought the energy was in the copper.
Right.
And then when Ralph beat it into my head you're wrong, kid, and I finally listened, my whole life changed.
Good.
Yeah.
That's amazing.
So energy is in the air. Energy is in the
It's
environment.
in the dielectric, and sometimes the dielectric is air.
pardon my saying so, but it sounds like the Vedantic school of thought.
The which?
Yeah, why are you bringing religion into this? But go ahead.
No.
We'll cut
There
this
is a
part.
philosophy that
Oh, yes.
the whole universe or the whole world is full of energy.
Yes. Well, it probably is,
It
actually.
probably is. Oh,
Oh, God, now you've got me thinking.
sorry for that side.
Oh, that's okay. Huh.
Well, I think this is a great note to end on, unless you have more stuff.
I just want to ask you something about the AI. What AI can do in the high frequency RF field?
That's yet to be seen, I'm afraid.
Yet to be seen.
For years, I was convinced that artificial intelligence would never come about because I thought of it incorrectly.
Mm-hmm.
And I thought what they were trying to achieve was to come up with a computer that could reason. That's what real intelligence is in humans. It's not what you know. It's not the knowledge you've gained. It's what you can do with the knowledge you've gained and how you can take two ideas, put them together, and come up with a third idea. That's the power to reason. And I was convinced that a computer could never accomplish that because it doesn't have that reasoning ability we have. I saw a video many years ago of a gorilla who they put a banana outside his cage. He pulled it in, he ate it. Next day they put one far enough away he couldn't reach it. There happened to be two sticks inside of his cage, and he was playing with one of them, and he was like, and he reached out and pulled the banana in. That's intelligence. He realized that he can take this thing and himself, the two things together, now he can get the banana. And I figured computers would never, but what they're doing, as you know,
Yeah.
is they're gathering data so that they have so much data stored away in memory that when you ask it a question, it can go through trillions of, if necessary, bits of information to figure out the most optimum path to weave its way down to get to the ideal answer. And there will probably be times when artificial intelligence will give us non-ideal answers. There'll probably be times it'll fall on its face, but there are times humans fall on their face because our reasoning abilities are not perfect.
Exactly.
So, but I think it's going to help us long term, provided we control it properly.
Right. So artificial intelligence, that's what I many times feel. The word intelligence being used with artificial
Yes.
is a mistake, but it has happened.
Yes.
So many mistakes can happen in electricity, like electrons
Yes.
having the negative charge.
Yes.
You
Right.
know.
Yes. Yes. Yes.
You see, so
Yes.
similarly, the artificial, basically what it is not replacing human intelligence.
No.
And
It's
it can never
supplementing.
have that. But
Right.
it is able to analyze huge amounts of data
Right.
in either a deterministic or an stochastic manner
Yes. Correct.
to produce very quick results.
Yes.
Which let us say
That are
is
very close, if not perfect, very close to perfect.
very close.
Yeah. Yeah.
So
Yeah.
that way it helps in decision making.
It supplements
and
our
learning.
intelligence and our knowledge.
And if you can make it learn,
Yes.
you know what you are looking for and
Right.
how it should do, then it does that even faster.
And then, like a human, as it learns, it gets smarter and smarter.
Right.
The more I learn, the better I become at everything I do.
Exactly.
And computers will be the same way.
So I have a feeling that AI is slowly coming into the electronics field.
Oh, I'm sure it's going to.
And it would definitely possibly come into the the high
There was a
frequency
panel
field.
at PCB West of people who talked about what is the future of printed circuit design if it starts to include AI. And there was no concrete decision made, but they talked about possibilities. Where could it be helpful?
Right. No, I think that's it then.
And it'll happen eventually. Yeah.
Okay.
Every PCB designer that I've talked to, the killer app for them is, someone looking over their shoulder telling them what you're trying to do is actually going to cause a lot of problems. So like kind of a guide, right?
Mm-hmm.
Right.
So they don't want someone to do the work. That's why you're
But they don't want to read the guide. Somebody needs to keep
Yeah.
on telling them as they're doing the work.
right.
So it has to be an online tool.
Right.
So they are working on a computer,
Right.
and some the guiding mechanism had to be there. That app has to run,
Yes, correct.
and as soon as he makes some wrong decisions, it has to warn
Yes.
him.
So
Something like that.
actively watching you as
Exactly.
you go, so it can cue you. Hey, you might not want to route that there. You might want to move it over there.
Right.
Yeah, that's
Yeah.
a good thought.
Yeah. I mean, we have DRCs, but DRCs are all rules based, and
Yes.
you can't have a rule for every single thing. It's not
No,
possible,
It is not possible.
right? So
It'll take enormous time to process if
Right.
you start having on very complex
Yeah.
kind of rules. And all
Right.
that stuff.
So I think an AI based kind of, and this sounds funny, but an
AI-based rule checking.
AI based rule
Yeah, no,
checking.
I think those will come and basically live.
Yeah,
you know,
it
almost
should be
online.
it should be live.
Yeah, it really should be. That's a really good point. I
Yeah.
hadn't thought about that. That's a really good point.
No, actually, I just thought about it right now, and I thought that something can be done about it.
That
Let us
is
see.
a really good
So
point.
some of the AI experts, I think, need to be contacted and talked to about.
You know, I really appreciate the startups in our business that they're trying to do something with AI. They themselves are not experts.
Right.
They're not experts at AI, and they're not experts at designing either. They're only like in their 20s.
Yes, and they're computer weenies who are, pardon the expression, they're computer geniuses in some
Right.
cases. But they aren't necessarily board designers or engineers or AI experts.
Or AI experts. So they're actually not the people to solve the problem.
Actually, electronic hardware design is not encouraged very much in these, the engineering curricula today in universities.
That's right.
It's
That's
a
right.
problem.
That's a problem.
Yeah.
Yes, it is.
They
Well,
have
I
to
think
learn
it's
it on the field.
I think it's going to change now that half the software is going to be written, by
Maybe,
AI.
maybe.
And that's a point.
If half your software is written by AI, then maybe now focus on hardware.
Yep, that's a good point.
Good.
Well, always a pleasure.
Thank you. It's a pleasure for me to be here with both of you.
Yeah, no, I thought it was
Thank you, Rick.
excellent discussion.
So did I. I
Yeah.
enjoyed it.